Welcome to the deep dive. Today, you're joining us for an exploration into something, well, absolutely fundamental to how your body holds itself upright and moves the stretch reflex.
Mhm.
We're going to unpack its anatomy. The physical structures involve the fascinating physiology of how it works, the neuroscience that kind of orchestrates it all, its crucial role in your postural control, and even some interesting connections to what's sometimes called body misalignment or Yugami.
Right.
Think of this as your shortcut to understanding the amazing automatic systems your body uses, well, every single moment.
That's right. And as always, we know you come from all sorts of backgrounds. Some of you might be pretty familiar with biomechanics, while others are simply curious about the incredible machine that is your body.
Yeah.
Our goal today is to take these potentially complex ideas and explain them clearly, avoiding uh, overwhelming jargon and hopefully sparking a few of those satisfying aha moments for you.
Yes.
We've really dug into a variety of research to bring you the key insights.
Okay, let's get right into it then. What exactly is the stretch reflex?
In simple terms, the stretch reflex is the contraction of a muscle in direct response to it being stretched, passively stretched. It's like an automatic counter mechanism, increasing the muscle's tension when it senses a lengthening force, all within its, normal physiological limits.
Okay.
Now, here's where it gets really interesting for understanding how our knowledge has evolved. For a long, long time, it was thought that the stretch reflex and the tendon reflex, that knee-jerk reaction your doctor tests, were essentially the same thing.
Ah, right.
Just different ways of activating the same basic spinal reflex arc.
But they're not the same, are they? That's where the work of those researchers, Marsden, Merton, and Morton, comes in, right? The three M's. Tell us about their pivotal discoveries.
Absolutely. The three M's, back in the late 1960s, early 1970s, these three scientists conducted some, well, really ingenious experiments in London. Remarkably, Marsden even used his own thumb muscle for some of these studies. Yeah. Their work provided definitive evidence that the stretch reflex and the tendon reflex actually utilize distinct anatomical pathways. They aren't just two different ways of triggering the same underlying mechanism.
And the key to unlocking that understanding was the difference in their timing, wasn't it? The latency of the response.
Exactly. They observed that the stretch reflex took a noticeably longer time to initiate a muscle contraction compared to the tendon reflex.
Mm,
In the thumb, for example, they measured a delay of about 45 milliseconds for the stretch reflex, whereas the tendon reflex fired off in roughly 22 milliseconds.
that's almost double.
Right. That near doubling of the time strongly suggested that the stretch reflex wasn't just a quick, direct loop within the spinal cord like the tendon reflex. It implied a more complex route for the neural signal.
Which naturally leads us to the neural pathways involved. So
Mhm.
what's the fundamental wiring for the stretch reflex to occur? Like the basic loop.
Okay, at its most basic, it involves a spinal reflex arc. Within your muscles are specialized sensory receptors called muscle spindles.
Right, the spindles.
These spindles are highly sensitive to changes in muscle length. When a muscle is stretched, these spindles send sensory information up to the spinal cord.
Okay.
Within the spinal cord, this information directly activates alpha motor neurons. These motor neurons then send a signal back down to the very same muscle that was stretched, causing it to contract.
Ah, okay.
This fundamental loop plays a crucial role in maintaining a baseline level of muscle tone and provides a really rapid automatic correction for sudden changes in your body's position.
That sounds like a fairly direct and immediate response, but you mentioned the longer latency earlier, hinting at something more intricate. That's where the concepts of short latency reflexes and long latency reflexes come into the picture.
Precisely. The very first rapid muscle response, occurring approximately 20 milliseconds after a perturbation or disturbance,
Uh,
is what we call the short latency reflex, or SLR.
SLR, okay.
This is largely attributed to that simple, direct, or as we call it, monosynaptic spinal pathway, meaning it's a very direct connection with just one synapse, or relay point, in the spinal cord.
Got it.
This SLR contributes significantly to the stiffness you feel in your muscles and joints. But then we have the long latency reflexes, or LLRs, which take a longer time to manifest after the initial stretch.
And these longer latency reflexes were what really intrigued Marsden and his colleagues, weren't they? They suspected the involvement of the brain.
Absolutely. Marsden and his team proposed that the signal for the stretch reflex actually traveled up to the cerebral cortex, the outer layer of the brain, responsible for higher-level functions, before heading back down to the spinal motor neurons to trigger that later muscle response.
So up and back down?
Kind of, yeah. This idea gained further traction with observations of stimulus-sensitive cortical myoclonus, where brain activity recorded on an EEG actually preceded the muscle twitch. So the initial quick reaction is mostly spinal, but these later responses bring the brain into the loop, making it more flexible.
So it's not just a conversation happening at the level of the spinal cord. The brain is also involved, potentially influencing the response.
Exactly. C.G. Phillips even coined the term transcortical stretch reflex to describe this concept, the idea that the reflex pathway goes through the cortex.
That's cortical. Okay.
And subsequent research by Tat and Lee identified the different long latency loops, which they labeled M1, M2, and M3. M1 corresponds to that initial spinal reflex we talked about.
Right, at the SLR.
But M2 and M3 involve the brain, specifically the motor cortex for M2 and potentially the cerebellum, which is crucial for coordination for M3.
What's fascinating here is that these longer latency reflexes seem to be much more adaptable to different situations compared to the quicker, short latency ones.
Oh, definitely. What's fascinating is that they can respond to a wider range of and more complex kind of arbitrary constraints than the more immediate stimulus-driven short latency reflexes.
Hmm.
This adaptability is really key to our sophisticated movement control. These long latency reflexes can be adjusted based on factors like your training level, the specific posture your body is in, and even during rhythmic cyclical movements like walking.
So it learns or adapts.
Adapts is a good word. This modulation involves descending signals from the brain, influencing things like presynaptic inhibition, which is a way of dampening the signal before it even reaches the next neuron.
Okay.
Neuromodulatory signals chemicals that can alter the excitability of neurons and even the gamma drive to those muscle spindles we discussed earlier.
So the brain can essentially fine-tune the stretch reflex based on what you're doing and the context of the environment you're in.
Precisely. And it's not just about these longer loops either. Even those seemingly simple short latency reflexes aren't entirely isolated in their action. Research has shown that they engage surprisingly complex circuits within the spinal cord itself, integrating information from multiple joints and even muscles in different limbs.
Really? Even the quick ones?
Yeah, it's a more interconnected and sophisticated system than we might initially imagine.
You mentioned muscle spindles earlier as the initial sensors of stretch. How exactly do they work with the motor neurons to initiate the stretch reflex? That's where alpha-gamma coactivation comes in, right?
Yes, the alpha and gamma motor neurons work together in a, well, beautifully coordinated way. The alpha motor neurons are the ones that directly cause the main muscle fibers, the big ones, to contract and generate force.
Okay, the force producers.
Right. The gamma motor neurons, on the other hand, don't directly produce significant force. Instead, they innervate those muscle spindles, effectively adjusting their sensitivity to detect stretch.
So they tune the sensors.
Exactly. What's clever here is that when your brain signals a muscle to contract via the alpha motor neurons for a voluntary movement, it often simultaneously activates the gamma motor neurons. This coactivation ensures that the muscle spindles remain sensitive to any stretching that might occur as the muscle shortens or if there's an unexpected external force.
Ah, clever.
It's a brilliant mechanism to maintain the reflex's ability to respond even during active movement and maintain muscle tone.
Okay, so we have this incredibly intricate system of reflexes. How does all of this contribute to our ability to stand upright and move around without losing our balance? That's the essence of postural control, isn't it?
Exactly. Stretch reflexes don't operate in isolation. They are integral members of a larger team of reflexes, including what we refer to as postural or riding reflexes.
Rail reflexes.
These different types of reflexes work in concert, constantly communicating and adjusting to maintain your body's orientation in space relative to gravity, control your balance, and ensure that your movements are smooth and coordinated. Think about when you're standing on a slightly uneven surface.
Yeah.
Those tiny, almost imperceptible sways you make to stay upright. That's your stretch reflexes constantly working in your leg muscles to correct those subtle imbalances.
Give us some specific examples of these riding reflexes in action.
Okay, consider the labyrinthine riding reflex. This reflex is driven by your vestibular system located in your inner ear. It senses the position and movement of your head relative to gravity.
The balance sensors in the ear.
Right. If you start to tilt or fall to the side, even if your eyes are closed, this reflex kicks in to activate the muscles in your neck and trunk, helping to bring your head back to an upright position. It's why if you stumble, your head often rights itself before the rest of your body fully reacts.
That makes perfect sense. What about other examples of these automatic postural adjustments?
Then there's the body-on-head riding reflex. This one relies on proprioceptors, those sensory receptors in your muscles and joints, giving position info specifically in your neck.
Ah, neck sensors.
They detect the alignment of your body relative to your head. If your body tilts or rotates, but your head stays relatively upright,
Hmm.
maybe because you're visually focused on something, this reflex tries to bring your body back into alignment with your head.
Like a gymnast.
Exactly. You see this beautifully illustrated by gymnasts who maintain a focused head position during complex rotations. Their body naturally follows to maintain that alignment. And of course, we also have the visual writing reflex, where your vision plays a huge role in orienting yourself and contributing to balance.
Now, this is where the connection to what some call body misalignment, or Yugami, really intrigues me. How might the stretch reflex system be involved in that?
This is a fascinating area where the intricacies of our neural reflexes and the balance of our musculoskeletal system really intersect. The underlying idea is that imbalances or dysfunctions within these very reflex systems can actually contribute to the development and maintenance of what is perceived as body misalignment.
So it's not just a matter of bones being out of place. The nervous system and these automatic reflexes play a role.
Precisely. Consider this. If the muscle spindles in certain muscles become excessively sensitive, we call this hyperactive, they can lead to a state of chronic elevated tension in those specific muscles.
Okay, too tight.
Right. This sustained tension can, in turn, cause a reciprocal inhibition, a weakening or reduced activity in the opposing muscles around a joint.
So one side tight, the other side weak.
Basically, yeah. Over time, these persistent imbalances in muscle tension can contribute to gradual shifts in posture and alignment.
That's a clear connection. Tight muscles literally pulling the body out of its ideal alignment. What other ways can our neural reflexes contribute to this?
Another crucial factor is the remarkable adaptability of our neural pathways.
Yeah.
If we consistently adopt certain postures, even if they aren't, biomechanically ideal,
Like slouching at a desk all day.
exactly, our brain can gradually recalibrate its internal sense of what constitutes straight or neutral. This new normal then becomes the baseline reference point for our postural and writing reflexes.
Wow.
So these reflexes might be functioning perfectly well in terms of their responsiveness, but they are operating based on an altered perception of alignment, effectively reinforcing the existing misalignment. It's as if the body's internal gyroscope has been subtly reset to an incorrect position.
So our habitual core postures can literally change how our brain interprets correct alignment and influence our reflexes. That's a powerful thought.
It is. And finally, we see the development of compensatory patterns. A primary misalignment in one area of the body, for example, a slight tilt in the pelvis, can trigger a cascade of secondary adjustments in other regions as the body attempts to maintain overall balance and equilibrium. Your lumbar spine might develop an exaggerated curve to compensate, which in turn could affect your thoracic spine and even the position of your neck and shoulders.
So it's a domino effect.
Exactly.
Yeah.
This creates complex, multi-level patterns of misalignment that can all originate from that initial imbalance and the body's ongoing reflexive attempts to find stability.
This really highlights the interconnectedness of our body and suggests that addressing these issues might require a more comprehensive approach.
Absolutely. If body misalignment can have a significant neural reflex component, then assessment shouldn't solely focus on static structural alignment. Evaluating the function and sensitivity of these reflexes becomes a crucial aspect of understanding the underlying issues.
Right.
This might involve specifically testing the excitability of stretch reflexes in different muscle groups and assessing how effectively the writing reflexes are functioning in various postures and during movement.
And if the nervous system and these reflexes are contributing to the problem, how do you approach treatment?
Well, treatment strategies can then incorporate techniques aimed at resetting or rebalancing the nervous system. This could involve modalities like vibration therapy, which can help to modulate the sensitivity of those hyperactive muscle spindles,
Okay.
or proprioceptive neuromuscular facilitation, often called PNF, which uses specific patterns of muscle contraction and stretching to influence the activity of the gamma motor neurons and improve neuromuscular control.
PNF. Got it.
Sensory recalibration is also key. Retraining the writing reflexes through exercises that challenge balance and proprioception, maybe using visual feedback, vestibular exercises, or training on unstable surfaces. This helps the brain establish a more accurate internal map of alignment.
Retraining the brain's map.
And of course, progressively realigning the body by addressing those compensatory patterns systematically, often starting with a primary imbalance and combining passive correction with active exercises to rebuild neuromuscular control and stability, is essential. The ultimate goal is to correct the fundamental neural and musculoskeletal imbalances to reduce the compensatory muscle tension that arises from these reflex mechanisms.
So it's a more holistic approach that considers both the physical structure of the body and the underlying control systems of the nervous system.
Exactly. Now let's shift our focus slightly and consider some of the factors that can influence the stretch reflex itself. It's not a static, one-size-fits-all response.
Right. We saw some interesting research points about the difference between the velocity and the acceleration of a stretch, and also how the initial length of the muscle can play a role.
Yes, research specifically looking at spasticity testing in children with spastic paresis has provided valuable insights here. It appears that the intensity of the muscle's reflex response, the peak electrical activity recorded in the muscle, the EMG burst, is more closely related to the velocity or speed at which the muscle is stretched. A faster stretch tends to elicit a stronger reflex contraction.
More speed, bigger reaction.
Pretty much. However, the speed at which the reflex action begins, the time it takes for that electrical activity to appear after the stretch starts, seems to be more influenced by the acceleration or the rate of change of velocity of the stretch. Higher acceleration tends to lead to a quicker onset of the reflex.
That's a subtle but important distinction. So a very rapid, sudden stretch might trigger a quicker and more intense reaction compared to a slower, more gradual stretch, even if both stretches reach the same final length.
Precisely. And it's not solely about the speed or suddenness of the stretch either. The initial length of the muscle when a stretch is applied also appears to be a factor. Some research suggests that if a muscle is already in a lengthened state, the subsequent stretch reflex might actually be reduced.
Really? Why would that be?
Well, one possible explanation involves the activation of Golgi tendon organs, or GTOs.
Ah, the GTO is another sensor.
Right, another type of sensory receptor within muscles. But these are more sensitive to muscle tension rather than length. When tension increases significantly, they send inhibitory signals back to the spinal cord, potentially dampening the stretch reflex. It's thought to be a protective mechanism to prevent overstretching or tearing the muscle under high load.
Interesting. So our body has these built-in feedback mechanisms that can modulate the reflex response depending on the existing state of the muscle. You also mentioned something called preflexes, these anticipatory muscle adjustments. Can you explain what those are?
Preflexes are essentially proactive anticipatory muscle activations. If you anticipate a potential disturbance to your balance or stability, say you're bracing yourself because you think someone might bump into you,
Yeah.
you might subconsciously increase the stiffness of the muscles around the relevant joints to prepare for the impact. These preflexes can help to minimize the effect of the expected disturbance.
So bracing for impact.
Kind of. However, they aren't always beneficial because they rely entirely on your prediction being accurate. If your prediction is off, those preflexive stiffening actions could actually make you more vulnerable to imbalance.
Ah, I see.
Think about bracing yourself too rigidly when walking on an icy surface. If you do slip, that stiffness might prevent you from making the small, quick corrective adjustments needed to regain your balance.
So it's a balancing act between being prepared for a potential challenge and being too rigid to adapt effectively to unexpected changes.
Exactly. And then we have the fascinating influence of our intended movements, our motor plans on these reflexes. Long latency reflexes in particular seem to be involved in both providing stability to the limb against unexpected disturbances and also in the rapid execution of pre-planned motor actions, sometimes called triggered reactions.
Two jobs at once.
It seems like it. Interestingly, at least initially, these two functions appear to be controlled somewhat independently within the long latency reflex pathway. For example, the specific direction of a target you're reaching for can influence the triggered reaction component of the long latency reflex, separate from its stabilizing role.
It's almost as if our brain is simultaneously managing different priorities, maintaining stability and carrying out our intended movement, and the reflex system is adapting to support both.
Precisely. And the story gets even more intricate. Even those short latency reflexes, which were once considered relatively fixed and automatic responses, can be modulated by factors such as extensive training, changes in your body's posture or configuration, and during rhythmic, repetitive movements like walking or running. Our nervous system is constantly fine-tuning these reflex responses based on the specific context and demands of the situation.
And the studies on unexpected landings really help to differentiate between the purely reflexive muscle activity and the pre-programmed actions, didn't they?
They did indeed. These experiments demonstrated that when subjects unexpectedly landed on a surface that didn't provide the anticipated ankle joint movement, like a false floor drop,
Oh, Ooh, tricky.
Yeah. The typical immediate burst of muscle activity in the calf muscles, gastrocnemius and soleus, that usually occurs right after landing was absent.
Interesting.
This strongly suggests that this immediate muscle activation is primarily a short latency spinal reflex triggered by the specific rotation of the ankle joint upon impact, rather than just a pre-planned muscle contraction initiated before landing. Of course, there is also pre-programmed muscle activity involved in preparing for a landing, but the very first rapid response to the actual impact seems to have a clear and distinct reflex component.
Let's delve a little deeper into the concepts of stretch reflex threshold and spasticity. I came across discussions of SRT and TSRT. What do these terms signify, and how do they relate to conditions like spasticity?
Right. Stretch reflex threshold, or SRT, is essentially the point often measured as a specific joint angle at which the stretch reflex is first triggered. This leads to the detectable onset of electrical activity in the muscle, which we measure using electromyography, or EMG.
Okay, the angle it kicks in.
Exactly. The tonic stretch reflex threshold, or TSRT, is a related concept that tries to estimate this threshold under conditions of very slow or even theoretically zero stretch velocity. These measures are often used in clinical settings to quantify the degree of stretch hyperreflexia.
Hyperreflexia meaning an exaggerated reflex.
Correct. An exaggerated stretch reflex, which is a common sign observed in conditions like spasticity, often resulting from neurological injury like stroke or spinal cord injury.
And why is accurately accounting for the latency, the time delay of the reflex, so important when trying to measure the SRT?
That's a critical point because there is that measurable time delay, the latency, between the moment the muscle is stretched and when we actually see the electrical activity in the muscle due to the reflex.
Yeah.
Failing to account for this delay can introduce significant errors in determining the actual joint angle at which the reflex initiated. Researchers have found that correcting for this latency, often by using the latency of the H reflex.
The H reflex.
Yeah, it's another type of spinal reflex test that bypasses the muscle spindle and directly stimulates the sensory nerve. Using its latency helps correct the SRT measurement.
Okay.
And doing this correction can make the SRT measurement less dependent on the speed of the stretch, providing a more accurate assessment of the underlying excitability of the stretch reflex pathway itself.
So a more precise SRT measurement gives clinicians a better understanding of how easily the stretch reflex is activated in someone experiencing spasticity.
Exactly. And while these quantitative measures are valuable diagnostic tools, it's also important to remember there's ongoing scientific debate about the fundamental mechanisms underlying hyperreflexia in spasticity. Some researchers propose it's primarily due to an increased excitability of the stretch reflex pathways themselves, while others suggest that an impaired ability to predict the sensory consequences of movement might also play a significant role. It's increasingly likely that it's a combination of these and potentially other factors that contributes to the complex phenomenon of spasticity.
It's remarkable how seemingly simple reflexes are actually governed by such intricate mechanisms and are constantly being influenced by a multitude of factors.
It truly is. And what's even more fascinating is that recent research has revealed that spinal stretch reflexes can play a much more sophisticated and supportive role in our voluntary movements than we previously understood.
Oh, so? I always thought voluntary movements were primarily initiated and controlled by the brain, kind of top down.
Well, it turns out that spinal stretch reflexes can efficiently assist in voluntary reaching movements by automatically counteracting unexpected disturbances to the limb. And what's particularly interesting is that the way these spinal reflexes respond to a perturbation depends on how your hand is currently interacting with the environment.
Really? Depends on the hand's interaction.
Yeah. For instance, if you are reaching for an object and your elbow is unexpectedly pushed into flexion, the spinal reflexes in the muscles around your elbow will react in a specific way. But that way is different depending on whether your wrist is simultaneously flexed or extended.
Whoa. That suggests a surprising level of integration and context awareness occurring even at the level of the spinal cord, not just a simple reaction.
Precisely. It highlights that the neural circuits within the spinal cord are not just simple relay stations for signals between the brain and the muscles. They possess a degree of complex processing capability. They can intelligently utilize the anatomical connections between different joints to contribute to efficient and coordinated control of the hand during voluntary actions. It's a beautiful example of how different parts of our nervous system work together seamlessly and often in ways we are not consciously aware of.
Wow. This deep dive into the stretch reflex has truly been illuminating. From the fundamental spinal reflex arc to the potential involvement of the cerebral cortex and its multifaceted role in posture, balance, and even seemingly voluntary movements, it's clear that this is a cornerstone of our motor control system.
Hmm.
And the intriguing connections to body misalignment or yugami offer another fascinating perspective on how our bodies function and sometimes experience imbalances.
Absolutely. The key takeaways for you listening are that the stretch reflex is far more than a simple, isolated muscle contraction. It involves a complex interplay of spinal and potentially transcortical pathways, constantly being modulated by a variety of factors like the speed and size of the stretch, the starting muscle length, and our anticipatory muscle activity.
Right.
Its critical role extends to maintaining our upright posture, controlling our balance against perturbations, and even subtly contributing to the efficiency of our voluntary movements. And understanding the potential for imbalances within this system to contribute to body misalignment opens up, well, exciting new avenues for both understanding and addressing musculoskeletal issues.
And for you, our listener, I hope this exploration has provided some valuable aha moments and fostered a deeper appreciation for the remarkable automatic intelligence of your own body.
Definitely. Consider this final thought to ponder. How might your everyday postures and the patterns of movement you habitually engage in be subtly shaping the neural pathways that govern your stretch reflexes? How might they be influencing their sensitivity over time?
Mm.
What could be the long-term implications of this continuous dynamic interplay between our habits and our reflexive responses for your long-term musculoskeletal health and overall well-being?
That's a great question.
We encourage you to become more mindful of your own postural tendencies and to observe how your body instinctively reacts to unexpected shifts or movements. It's an ongoing feedback loop, and increasing your awareness of it can be a powerful tool for understanding and perhaps even influencing your own physical state.
Thank you for joining us for this deep dive. Until our next exploration, keep pondering.